Okay, so we're going to be working on rational exponents. Rational exponents meaning that you have to work with your exponent rules, which are the ones that we saw just yesterday. So we have seen that an exponent can be an integer. So we know that 5 to the power of 2 is equal to 5 times 5, which then equals to 25. So that should be relatively easy. We've also seen negative exponents. And when we have negative exponents, we basically create the fraction over 1, and you take the reciprocal of that fraction and make the exponent positive. So what that looks like is 1 over 5 times 1 over 5. I'll leave it in brackets. You don't have to. You could put a times symbol. And that gives you 1 times 1, which is 1, and 5 times 5, which is 25. We've also seen exponents of 0, and anything to the power of 0 will be equal to 1. So what happens when you have a fraction? So we have positive exponents, negative exponents, exponents of 0, but the key word here is rational exponents. So rational numbers as exponents. So let's take a look at what's going on here. If we have 5 to the power of 1 over 2 times 5 to the power of 1 over 2, that means that the bases are the same. So based on our exponent laws, we have to keep the same base and add these exponents. So basically 1 over 2 plus 1 over 2 is 2 over 2, and 2 over 2 is equal to 1. So 5 to the power of 1 is 5. Now, we also know that the square root of 5 times the square root of 5 is equal to the square root of 25. This is based on your radical unit that you did, the first unit I believe. And the square root of 25 is equal to 5. So, similarly, if you look at these two things, it means that 5 to the power of 1 over 2 times 5 to the power of 1 over 2 is equal to the square root of 5 times the square root of 5. So essentially what you're looking for here is to know that if these two things are equal, it must mean that the first part is equal to the first part here, and the second part is equal to the second part here, which means, therefore, that 5 to the power of 1 over 2 is equal to the square root of 5. So it's a little bit interesting to find out. The proof is a little bit more difficult, but this is what it means, that when you have an exponent with fractions, you're going to create a root. Okay, not always a square root, but you're going to create a root. So let's see what's happening with this other example, see if this can help a little bit. So we have 7 to the power of 1/4 multiplied 4 times. So we have the same base here, the base is 7, and we're multiplying the same bases. So it means we're going to keep the same base, and we're going to add these exponents. So 7 to the power of 1 over 4 plus 1 over 4 plus 1 over 4 plus 1 over 4. If I add all the numerators, since the denominators are the same, this gives me 7 to the power of 4 over 4, which is 7 to the power of 1, which is then equal to 7. And if we do the fourth root of 7 times the fourth root of 7, so we're doing that 4 times, it basically tells us that it's the fourth root of 7 to the power of 4. And we know that when you have a root and an exponent that match, the root and the root and the exponent cancel out. So we get an answer of 7 here. So I don't know if that was clear or not, but just try to remember that when you're trying to solve for x, let's say, and you have a squared in the way, you just do the square root. Well, the square root always has a 2 here, but it's invisible. So that's why you never see it when you're doing the square root. But when you're doing the fourth root, you have to mark it down in the right inside the radical. Okay, so in general, we have it therefore here, 7 to the power of 1 over 4 is equal to the fourth root of 7. So there's a rule for this. Okay, so if you didn't understand what I just did, you don't really need to worry too much. You'll never need to prove it. You just need to understand that for any number n, where n cannot be equal to 0, because that's the denominator and that sets a restriction, when you have an exponent that's a fraction, you create a root. it's the nth, so you put the denominator inside the root, you put the number, the base, on the inside, and this one here becomes the exponent right over here. Okay, so it basically looks like the nth root of x. That's what you need to remember. So any exponents that are created with fractions, you have to make a root. So the denominator of the exponent becomes the index of the root. So in this case, the index is n, so it's the nth root. So let's move on to seeing what this question is asking here. What if the fraction exponent doesn't have 1 as the numerator? So that's a really valid question, because up here, we kind of got rid of that exponent. Exponent of 1 doesn't really do anything, so we just keep it as x. So what happens if the exponent is not a 1? So let's investigate by seeing some examples here. We know that the power of a power law says that if you have an exponent and another exponent, that you multiply those exponents. Okay, so here's the example of what it looks like. X to the power of a, then to the power of b equals x to the power of a times b. So 9 to the power of 2 over 3 can be thought of as 9 to the power of, so we'll just look at this part right here. So 2 over 3 can be thought out as 1 over 3 times 2. So if you look at it that way, you'll know that you're creating a numerator of 1. So we're going to rewrite that. We're going to put a bracket here. 9 to the power of 1 over 3 to the power of 2. We know that when we have a fraction as an exponent, we create a root. You leave the base inside the radical, and you take the 3 and you put it right here. So remember that the 3 is your index, and it goes right kind of inside the radical. We can't forget about that exponent of 2. So we're going to put it right there. So what we're going to do is we're going to evaluate this expression here. So this expression becomes the third root of 81. Don't forget that when you have radicals, you have to simplify them. So to do that, you have to know that 27 times 3 gives you 81. And in this case is the third root of 27. So 3 times 3 times 3 is what you're looking for. So that's why I split this up with the number 27, because that's the third root. The third root of 27 is equal to 3. So it's not the same as doing, there's a lot of 3's in here. So it's not the same thing as doing square roots. You can't split up, you can't do the square root, you have to do the third root. So this might need a little bit of work as well. It's a little hard to explain without having more examples, but let's see if it clears it up as we go along. Okay, so in general, oh, I forgot an example here. So 6 to the power of 5 over 4 can be split up as 1 over 4 times 5. So if you're okay with splitting that up, you'll understand that this means that it's 6 to the power of 1 over 4 to the power of 5. And when you have an exponent that's a fraction, you want to turn it into a root. It's the sixth root, sorry, not the sixth root, it's the fourth root of 6, and all that to the power of 5. So that's what that looks like without having to fully evaluate this. These are the kind of examples that we'll be working with. So what you just need to realize, this is just an investigation. This is the important part right here. So when you have an exponent that's a fraction, but the top number is not a 1, you create a root. Okay. You put the base inside the radical. You put the denominator, as the index, and you put all of that to the power of m. So what that looks like in the end is the nth root of x to the power of m. Okay, so that's what you need to look at. If you understand anything, nothing but that, that's what's important. So once we do the examples, we'll have to look at that. And then we'll have to look at the examples where the numerator is a fraction. So note that it doesn't matter if the exponent is applied first or last. Okay, it doesn't make a difference. Where n is a natural number and x is greater than 0, when n is even. So we can't have a negative square root, so that's why they're saying that x has to be bigger than 0. The minute your x is negative, that means you have a square root that's a negative, and that just doesn't make any sense. So note that you can take the odd root of a negative. So what I just said, you can't take the even root of a negative, but you can take the odd root of a negative. So if you realize that the third root at -8, I'll tell you what the answer is. It's -2. And that's because -2 to the power of 3 is equal to -2 times -2 times -2. And that gives us -8. So you're allowed to have an odd root of a negative, just not an even root of a negative. So that's the key word here. Okay. What if the exponent is a negative fraction? So we saw negative exponents, but now we're looking at negative fractions. So basically what's happening here is that we have to get rid of that negative exponent first. So we're going to create a fraction, just like we did yesterday. We're going to use the reciprocal of that fraction and make the exponent positive. Now you recognize that the exponent is a fraction, so right away you want to create a root. You want to take the denominator and put it as the index. Take the base, which is actually 1 over x, and then all this is to the power of the numerator, so to the power of 1. But we don't really need to the power of 1. It only changes when you have a different numerator here. So it's the nth root of 1 over x to the power of 1, which is equal to 1 over the nth root of x. Now, to explain this, is basically you're taking the root of the top number here, which is 1, and the nth root of 1 is just 1. Any root of 1 will always be 1. So then I just simplified this to put the radical in the denominator. So this all makes it more complicated once you have negative fractions that don't have a 1 at the top. So if we take a look at this example here, we're going to take the negative exponent and get rid of it. So we're going to create our fraction. We're going to flip our fraction and make the exponent positive. Now we realize that the exponent is a fraction, so we have to create a root. So to create the root, don't forget that this part is your index. This part goes inside the root, but this time I need a bracket, and I need to put it to the power of m this time, because it's not 1, it's to the power of m. To simplify this, we know that any root of 1 will always be just 1, and 1 to the power of anything is always just 1. So again, we leave the top as just 1, and then we have to figure out this last part right here. So we have the nth root of x and all that to the power of m. And if you simplify that just a little bit more, we want to get rid of those brackets. It's 1 over the nth root of x to the power of m. Again, pretty confusing until you start doing some actual examples. Just keep following through and see if you can just push through this content. So we're going to go ahead and start some examples because I feel like it might help to do a couple examples. So 27 to the power of 1 over 3. So what happens here is that we have an exponent that's a fraction. And when we have an exponent that's a fraction, we create a root. We put the base inside the root. We put the denominator as the index. And we put all this to the power of 1.